Hey, all right. No, actually, all right. I'll try to do this with the headphones on. I got new headphones and they're like they insulate the sound really well, so it feels really weird when I talk. But all right, so let me put up a warm up. So let's see. Right. So for each series, uh, find the radius of convergence and the exact interval of convergence. Um, so the first one is the sum n squared x to the n. Well, okay, they don't give indices. I'm going to omit them too, just because it's good to get used to not caring about the starting index when it's not relevant. And then the next one is the sum of 2 to the n over n squared x to the n. The next one is the sum of square root of n x to the n. And then the last one is the sum of 1 over n to the square root of n x to the n. Yeah. Okay, I think that'll be it for the warm up. So yeah, let's say resume at 5:17. Okay, so let's take a look at these. So I honestly think that, so after you do enough practice with these kinds of series, you should kind of get to the point where you can like pretty much just look at it and tell what the radius of convergence should be, and also tell whether it converges at the two endpoints. At least when the coefficients are just like very elementary functions, right? Where it's like, okay, you have some powers of n, some multiplication and division, some exponents, right? And stuff like that, or maybe some logarithms or whatever, but no like weird messed up like combinatorial functions or anything like that, with complicated definitions. It's all just like very familiar, functions that we've known since grade school. Then in all of these situations, you can kind of just look at it and figure it out. So here, like, what do you guys think the radius of convergence of the first one is?
It should be 1.
Yeah. And if you write down, like, if you actually write down, an to the 1 over n, you get like n to the 2 over n, and then you can kind of tell that that approaches 1, because we know that n to the 1 over n approaches 1, right? That was like one of the early sequences that we proved has the limit 1. But here's how I think about it when I look at it, which is just that like if an is built only with polynomials in n, then r equals 1 pretty much always. Like if you're only allowed to take n and do the operations of like multiplication, addition, subtraction, and division, right, to build up the expression for an, then the result is always going to be something where the nth root approaches 1. And that's just because like polynomials just don't like change fast enough relative to exponential functions, right? So so you can pretty much just look at this and like instantly tell that it's going to have radius 1. And then of course the sum diverges for x equals plus or minus 1, because the absolute value of an approaches infinity, right? So there's no way the sums could converge when x is plus or minus 1. So that's the first one. This one, the second one, what do you guys think?
-2 to 2, and then -2 is open. Wait, 2. Forgot it, but I did. This doesn't look if it's close.
You're close. You're close. But it's not -2 to 2.
Oh.
Right, because the radius. Okay, you're looking at like an, right? So, the nth roots of an approach 2, right? But remember that the radius is like the reciprocal of that. So yeah,
okay.
It's just like in this case, because it was 1, it doesn't matter whether you reciprocate or not. But yeah, so if you kind of think about the exponential behavior of an, you want to like do 1 over that to get the radius. So, but you're right. So in this case, it's 1/2, right? So you kind of correctly identified that like the n squared just doesn't do anything to the radius, right? So if there's like an exponential function floating around, then that kind of dominates the entire behavior. If that's like the biggest thing in the expression, right, then that's kind of all you care about. Yeah, and then sorry, what were you saying about the endpoints?
I guess it doesn't matter because I checked -2, so.
Oh, sure. Okay.
So, yeah, but I guess what I found was B. I guess is that what I found? Or beta.
Yeah, you found beta. Yeah.
Oh, beta. Yeah.
Yeah. Right. Yeah, that's what you found. Yeah. So basically, okay, mentally, like what I do when I try to think about what happens at the endpoints is it's like I literally just take whatever the exponential behavior here might be, and I just like ignore it, right? Because the thing is that like once x actually equals plus or minus r, then the whole point of like the computation of the of r itself is that like at that point when x is plus or minus r, then x to the n is canceling out like all of the exponential behavior, right? So then it's like if x is like plus r, then if there's like alternating signs in the coefficients themselves, then you get like an alternating series. And if x is minus r, then if there's or sorry, if x is minus r, then you'd get like a normal series. But if there's no alternation in the coefficients, then when x is plus r, you just get a normal series, and when x is minus r, you get an alternating series. So then you just have to think like about what's left over after you delete like the exponential thing here. So it's like if you ignore the 2 to the n and pretend that it's 1, right? Because when x is 1/2 or plus, when x is like plus or minus 1/2, the 2 to the n's are going to cancel out. So you either have like 1 over n squared, or you'll have negative 1 to the n over n squared, right? But the thing is, because the n squared is big enough, it actually doesn't matter whether it's 1 or negative 1 to the n, because both of those series converge, because 1 over n squared converges absolutely, right? So
Closed.
yeah, so in this
Okay.
case, it's negative 1/2, 1/2 closed. Yep. Yeah, so like you can actually get like pretty fast at just thinking about these and just looking at them and kind of telling what's going to happen. And I think it's actually a useful skill to have, because, you know, if you can do that quickly, then it helps you like mentally visualize like in more complicated situations, you know, what might be happening, I think. So yeah. Anyway, how about the next one?
Is it 1?
Uh-huh. Yeah.
Okay.
Yeah, and it's kind of the same thing as here. So it's like here we were only talking about polynomials which technically only involve integer powers of n, but really it's like if an is built with only constant powers of n and like plus minus times divides, right? Then r is 1. But here again, like in this situation, the absolute values of an themselves approach infinity, so it's going to be an open interval on both sides.
So intuitively, we should always just be comparing it to like n to the power n. Like, how is it compared to an exponential growth?
Yeah, like a constant to the power n. Yeah.
A constant. Okay, cool.
Yeah, it's like 2 to the n or like 3 to the n or just a to the n, like a to
Just
the
in
n
our
in
heads.
general.
Okay.
Is kind of like the situation where the an is like some constant raised to the power n. That's when you're going to get like an actual finite radius of convergence that
Okay.
isn't just like, you know, 1 or like 0 or infinity or something like that, right? So like down here, what do you think the radius is going to be? So I think what you said, like comparing, right? Comparing to an exponential function is a very valuable, that's like totally the right idea. So like, how would you say that this function compares to like an exponential function?
It would be faster than
Yes.
something. Yeah.
Right, exactly. And it's faster, right? It's not just faster than like a given exponential function, right? It ends up being faster than every single exponential function you could possibly write down, right? Because if you think about it, like one way to sort of verify that, like in general, as a rule of thumb, if you ever have like n raised to a power that's like an increasing function of n, usually that's going to be faster than any, or no, sorry. No, it depends on what kind of function. But if it's like any power of n up here, for example, so like square root of n or like n squared or just like n to the 1 over a million or whatever. If it's like log of n, then that's a different story. But in this case, it's square root of n. So, but another way to think about it is like you can rewrite this as like e to the square root of n times log of n, right? And so this ends up. Wait, actually, let me think.
R is infinity in this case, right?
Hold on.
Oh yeah.
Wait a minute. Am I just wait? Maybe I messed up. Maybe I made a mistake here. Hold on. Yeah, I thought R would be infinity. Maybe I got cavalier about this. If it's n to the square root of n, then well, okay. The easiest thing to do is just actually write down. Oh, actually, maybe R is actually 1 in this case. Sorry. I guess I'm a little bit rusty with these or something. Hold on. Yeah, because an is like, so this does not actually grow faster than exponential functions, I don't think, because this is like an to the 1 over n is like 1 over n to the 1 over square root of n, right? So the question is, so this is like 1 over e to the log of n over square root of n, right? I didn't get this wrong, did I? This is right.
How'd you get
yeah.
1 over? How'd you get 1 over?
Well,
n to
because
the 1 over square root.
So this is like n to the minus square root of n, the 1 over n, right? And then this is n to the minus n over square root of n.
I see.
Or so, no, I mean, sorry, square root of n over n. Yeah. And so that's n to the minus 1 over square root of n. Yeah.
Okay.
So then this is, so this actually approaches 0. So this whole thing actually approaches 1. Yeah, sorry. Okay. I got tripped up. Weird. That's never happened to me before. All right. Anyway, well, okay. So maybe it helps to be careful sometimes. So R is 1 in this case. All right. Yeah. So R is 1, and then okay. Let's see. So the question is, does the sum of so clearly when x is -1, right, it should converge because then you get an alternating series. But when x is 1, the question is, so does the sum, I'm going to erase this thing now. So does the sum of 1 over n to the square root of n. Oh, well, this definitely converges just by comparison to 1 over n squared, the sum of 1 over n squared when n is greater than 4, right? So it should be closed on both sides, I believe. Okay, yeah, sorry. I'm sorry I got mixed up here. I don't know why. So this one, I guess this is like, these can be kind of like dicey. But okay, one thing I will say is that if you ever have anything in any function here, so any function here that grows faster than n will give r is infinity, right? Because then or like so anything that grows at least as fast, I guess I should say, at least as fast as n. If you have like 1 over n raised to a function that grows at least as fast as n, then r will automatically be infinity. And that's just because you'll have something that grows faster than any exponential function, like I was trying to say before. So I guess it's just when the thing up here is like dubious. You have to be more careful. All right, anyway. Any questions overall about this warm-up exercise?
I just wanted to say that yesterday's discussion is on private. So.
Oh man, I'm sorry. Yeah, okay. I'll be more. Yeah, I'll try to be more careful about that. That's weird. Wait, I thought I set. I thought I. Oh, maybe it's because I was like flipping between trying to make it like self-publish itself at a specific time and just like setting it to public immediately. I don't know. Whatever. I'll figure it out. Yeah, I'll fix that as soon as this is over.
Thanks.
Yeah. Any other questions? Or also like questions about, any of the material so far. I think this particular area is like probably one of the, most familiar and simplest bits of material throughout the class so far. Because like I said, hopefully most people have seen at least something resembling this in like a calculus class or something like that. So
a quick question about pointwise convergence. Does
oh yeah,
pointwise convergence say anything about like the continuity of f? Because it doesn't imply I guess it doesn't imply uniform convergence, but does it say anything
right.
about I guess because you can take each point, but yeah, does it say anything about continuity?
Well, so to answer that question, I would ask you to think about the example, right? The example that was given at the end of the lecture, which was that function, like
1 over absolute value of x or something.
Yeah, or like 1 minus absolute value of
1
x
minus, yeah,
raised to the n power, right? Fn was this. So Fn converged pointwise where f of x was what function? So when x is non-zero, and remember x is in like -1, 1, right? So when x is non-zero, then this is a number strictly less than 1. So Fn of x eventually converges to 0, right? But if x is 0, then this is just 1. So Fn of x actually converges to 1. So we get the limiting function here was this. So 0 when x is not equal to 0, and 1 when x equals 0, right? And so f is not continuous at x equals 0, even though each Fn is continuous there.
Okay, cool. Mm-hmm. And the reason you took out 0 wasn't for continuity.
Oh yeah, that was like, so yeah, that was kind of because I was trying to like fit this into the sort of the whole like the framework that they give at the end of section like 22, where they turn a certain space of functions into a metric space, right? The way they defined that metric space was it was like the set of like bounded continuous functions. And so the thing is, what I was trying to show is that like in like C of S, it's possible to have a sequence Fn converging pointwise to F, even though Fn does not converge to F as a sequence in C of S, okay? Because remember, so it's like once you turn C of S into a metric space, then we inherit a concept of convergence from the definition that we made for sequences of points in a metric space, right? So we defined what it means for a sequence of points in a metric space to converge, right? So it's possible to actually come up with a space of functions and a metric on that space that turns it into a metric space such that like you can find a sequence of functions in the metric space and another function in the metric space itself, right? Such that like this sequence of functions actually converges to this function pointwise, but when you use the definition of convergence for a sequence in a metric space, this sequence does not converge to this function or to any function, basically, right? And so so that was why I just threw out the point 0, was because that way, once you throw out the point 0, then you can say like, so if S is like -1, 1 without the point 0, then like Fn converges to F pointwise, where Fn is the, well, Fn is what we defined before. So each Fn is like in C of S, and F of X is just 0 for X in S. So F is also in C of S. So I wouldn't be able to say that F was in C of S if I was still including the point 0, because the whole point of the example was that we made it so that F itself wasn't actually continuous at 0. But once you throw out 0, then F is just literally just 0 everywhere. So then F is continuous on this set, and that means that it's actually an element of C of S. So then it's like we have this like sequence of functions in C of S and another function in C of S, and this sequence converges to this function pointwise, but does not actually converge to this function as a sequence in the metric space C of S. That was kind of the point I was trying to make with this whole thing, and throwing out 0 and stuff.
And that makes sense. Cool.
Yeah. Good question. I mean, that I was kind of worried that wouldn't be like particularly clear, but I just didn't really. I don't know. It's hard to like really be careful and phrase this idea in like a really structured way. But anyway, to make it clear like what the point of what I'm saying is, I guess it's kind of hard because it's a very nuanced point. But I mean, whatever. All right, so let's go ahead and do another exercise. I mean, unless there are more questions. Okay. So let's let's do this one. Actually, yeah. Sure. Let's try this. So let Fn x equal nx to the n for x in 0, 1. Show that, well, the limit of Fn of x equals 0 for x in 0, 1, and b, the limit as n approaches infinity of the integral from 0 to 1 of fn of x is 1. So yeah, I'll go ahead and make a little room. So yeah, we can resume at like 5:50. All right, so hopefully this wasn't too difficult of an exercise here. So I believe, well, let's see. Okay, let's look at part A. Right, so we want to say the limit of n x to the n equals 0 for x. This is, of course, the limit as n approaches infinity. For x in 0, 1, right? And, you know, well, so I think there's actually, let's see. I think there's, well, one thing you can say actually is like, okay, the nth root of n x to the n is n to the 1 over n x, right? And that converges as n approaches infinity to just x, right? So if x is less than 1, then I think there's a theorem from section 9 that just directly tells us that this means, hold on. Is there? Well, actually, one thing you can say, this is kind of like hacky. There's probably a better way of doing this. I don't know why I'm kind of blanking right now. But one thing you can say is that, so then the series of nx to the n converges, right? That's by the root test. so nx to the n has to approach 0, right? Because that's just a necessary condition for a series to converge, that the terms approach 0, right? So that's one way of doing it. There might be a better way of doing it, like I said. I don't know. What did you guys come up with? Anything different? Like, I kind of feel like this is like overkill. We shouldn't have to say this, but
That's actually what I was thinking.
oh yeah.
Like making a series and using root test.
Yeah, okay. Yeah. I mean, it's a reasonable way to do it, you know. It's just like, I don't know. It seems like it should be easier to just somehow express the intuition directly that like x to the n obviously just decays way faster than n grows, but whatever. It's not worth the effort right now, I think. So that's that part. And then the second part is like pretty easy. But the point, right? The point is that there's like a moral of the story. So I'll get to that in a second. But right. So in the second part, you can just compute the integrals directly. So the integral of nx to the n dx is like n over n plus 1 x to the n. And so, all right, and then you evaluate at 1 and 0. And so that just gives you n over n plus 1. And this clearly approaches 1, right? So the point is, right, the whole like point of the exercise is that there's this like takeaway, right? Pointwise convergence Fn to F does not guarantee that the integral of Fn from, you know, A to B, let's say on A, B, converges to the integral from A to B of F. Actually, I'm going to just even delete this dx. I hate dx. No dx's. Later on, when we actually define integrals, this is actually the notation that we'll use. But anyway, so So in this case, right, we had the, like, obviously the integral, oops. The integral from a to b of f in our case would just be 0, right? Because f would just be like the constant function 0 on this set. On the closed interval, it's like the function 0, and then at one point, which is where x equals 1, it's like, I guess it's like infinity. So it's not really defined on the closed interval. All right, okay. So maybe I should be more careful. Let's say, I don't know, a, b, whatever, right? So in this case, f is just 0, constant. And so the integral of 0 to 1, the integral from 0 to 1 of f of x is just 0. But all of these integrals were 1. And so the reason is just that, like, you know, like the area keeps getting like more and more concentrated. Oh, maybe I should be more like, so like, right. Something like that. I don't know. Right. The area gets concentrated at x equals 1. This will end up being impossible for uniformly convergent sequences. So uniform convergence will like prevent stuff like this from happening, basically. So that's another like nice property of uniform convergence that makes it, you know, one of the things that we're interested in studying. So any last minute questions? Okay, well, in that case, I think that'll be it for today. So see you guys tomorrow.
Thank you.
Yep.
Thanks.
Thank you.